Recording, sharing, starting. Okay. So a little bit of review first. We're talking about these soil forming factors, right? Our CLORP soil forming factors. Really, the important thing about this whole lecture series is that all of these factors together explain why the soil looks the way it does. We talk about processes first. That explains the how. CLORP explains the why. Our soil forming factors, of course, our climate, and talking about a comparison across these soil forming factors, if we're looking at multiple soil pits or just considering soil within the environment with differences in these factors, we would say a comparison of climate is a climato-sequence. Comparison of organisms would be a biosequence, like our San Dimas example. A blank canvas of soil laid down at the same time experiencing different vegetation coverage. Relief was where we ended last time. A comparison of relief may be a series of soil profiles across a hill slope. That's what I think about a lot, planning field trips and stuff, or looking for variation. So if I'm looking for interesting places to look for differences in soil, I'm thinking about upslope, downslope. I'm thinking about a topo sequence. Really, this is so commonly studied in soil science. The special word for it is a katina, for comparison across relief. Today's topic, parent material, my number one favorite. We'll cover what the comparison across parent materials is next. And then on Thursday, we're going to talk about time as the final soil forming factor. And speaking of time, it's almost time for our first test. It's not this Thursday, but it's next Thursday in the lab section. You guys have been doing a good job with the Canvas review quizzes, just as a way of thinking about the material outside of class, thinking about what the important concepts and the takeaways are from maybe what we talk about in lecture. So really the best way to prepare for the test then is to work through those Canvas review problems, maybe expecting a little more open-ended or short answer questions on the test. We're going to do the time lecture on Thursday. Tuesday, a week from today in lecture, we're going to do a review activity here in our lecture meeting at 11. I'm unsure about a Zoom option for that. We're going to play a review game that I, in the past, haven't thought translates very well on Zoom. So probably a plan to attend in person next Tuesday if possible. And then Thursday in lecture, I might do a little preview of what's to come in the next units. We get a little more into like soil chemistry, soil mineralogy from that perspective. I might do a little preview of that, but then it'll be no new content. So after this Thursday's lecture, we're gonna wrap on like our first unit or the content for test one. The review is gonna be a little intense. It's gonna be like trivia questions, asking about everything possible that I've covered. It will not be the same standard of information. We're gonna talk about everything pretty much on Tuesday. I'm not gonna test you on everything necessarily. Speaking of everything, if you're on a list of everything that we've talked about in lectures, all the just the list of topics posted to Canvas now is our test one topic list, topic outline. Not necessarily a practice or like a study guide necessarily, but it's just a list of the main points, I guess, from each of our past lectures if you want to just review on some of the takeaways. And we got 2 new quizzes as well. The quiz from last week's content, I just put it up last night on Canvas. You have until next Tuesday to take that, as well as the topics we're going to cover today and next Thursday, our paramaterial and time quiz. That's also ready for whenever you guys want to take it. So the test itself, like I said, is going to take place in the lab section. So we'll meet in the soils lab at 1:30 like normal, or whenever you get out of class. You'll have the whole entire time to take it. That's a 4-hour block. Usually it takes students about 1 hour. So feel free to use all the time that you wish. I will be there the whole time if needed. We'll do a lecture portion of like multiple choice, true or false, and then short answer questions towards the end. And then there also will be a lab component, probably involving soil texturing, maybe a soil structure identification, maybe looking at a monolith or two. I told the second group last week out at Parker Farm, since we were such big fans of the really strong, coarse, prismatic structure in the Parker Farm pit, that I wouldn't be able to resist not giving you one of those Parker Farm prismatic structures as an unidentified mystery sample for soil structure. So if you got to come along on the Parker Farm field trip last week, that may be a little bit of an advantage for recognizing prismatic structure, but we also had practice doing that in our lab stations a couple weeks ago. Questions about that before we move into our topic today? People online, we got a lot of you today. Drop them in the chat or just feel free to speak up as needed. No, that's not my joke. That dates back probably as long as we've been describing soil horizons itself. Kind of can't resist, but talking about sea horizons, talking about parent material, kind of reminds me of my own parents and my own family sometimes. How I love parent material the most. I love my family a lot, and my parents, you could say, are definitely the sea horizons because they're the great material that my siblings and I all form from. And if I were to assign them two different parent materials, I would say they're both glacial till and glacial outwash, because not only are they the two that I love the most, it's that glacial till is usually a little less organized than glacial till is, and that's my dad and my mom together, so they're the till and the outwash. But since those are my parents, they're soil profiles. I would say my sister is an aridisol, not because she's particularly has a dry or boring personality, but she lives in Arizona. Okay, desert soil. I think aridisol is appropriate. She works for Bank of America as like a corporate credit analyst, like she doesn't make decisions on loans, but like she's assembling information that goes to somebody higher up that will decide if a company deserves a loan or not, which I think is, I'm sorry, I think that's a boring job. So she gets the dry one, the aridisol. Me personally, I put myself as an andesol because in any andesol profile, there's two distinct halves. There's the underlying parent material, which is, whatever the soil formation, the soil environment was like before, whatever my own life, my own personality was like before I had soil science. And then there's the addition of this new parent material, this new, much more interesting, much more exciting aspect of my life, which is soil science. A dramatic change to something much more interesting and exciting, if you will, the volcanic ash. But then lastly, I have my little brother. He's the entisol because there's not a lot of soil development going on there. No, maybe that's not so fair. I'm very proud of my little brother, of course. He was, we're all 2 years apart. My sister's 2 years older. My brother's 2 years younger. He just got out of the Peace Corps. He spent 2 years in Africa doing agriculture. I mean, his major in undergrad was like in international relations. He's very much I'm a natural world person. I love soils, I love environment. He's a human world person. He loves like governments and international relations and politics and all that stuff. He wants to work in an embassy, be a diplomat. So he joined the Peace Corps kind of as a career move. Little did he know that he'd be doing Peace Corps agriculture, like consulting with farmers and growing crops and doing cover crops and crop rotations and using the legumes, the nitrogen fixing crops, and working in these small cropping systems in rural Africa. But now he's in grad school at Notre Dame. So he probably deserves a little bit more. He deserves a B Horizon now. His name is Andy, though. He goes by Andrew now. So maybe that's andesol and I need something else. But a beautiful soil profile family, if you indulge me. That's enough about the Tietzes, though. Today's topic, what we're actually talking about, parent material, of course, is the material that any soil forms from. And really important because it dictates the soil chemistry, the mineralogy, the physical properties. It determines a lot about a resulting soil profile, much the same way that genetics come from our parents. The way that Paul McDaniel, our old pedology professor here, wrote about it in the textbook, at least, is that you can't build a wooden house where only bricks are available. You can't build a brick house where only wood is available. It determines a lot about a soil profile based on the inputs and the material, like the sediment that's available in the first place. It's possible that soil profiles can have multiple paramaterials when you have different geologic history, geologic events, sediment deposition taking place. I suppose that's where my analogy breaks down because I only have two parents. But changes in paramaterial can be really exciting. And more than anything, or really the reason that I love paramaterial so much, that I love soil science in general so much, is that these paramaterials specifically tell the story of the soil. I feel like every soil profile tells a story. If you know what to look for, if you know something about soil description, and you're looking at a soil profile, you can learn a lot about what has happened here on this landscape, the history of the environment, the local geologic history, just by interpreting this story in the soil profile. That's what makes me so passionate about this. So if we're going to start kind of covering all these different paramaterials, I want to show you an example of them, how to recognize them, fun facts, reasons to be excited about it. Where should we start? How about we start at rock bottom, work our way up. A rock bottom paramaterial, when we're forming soil out of pure bedrock, we call that our residuum. Residuum paramaterial just means soil formed in place from the bedrock. When this happens, you're very likely to contain rocks or coarse fragments in the profile. You're just inheriting the paramaterial's properties, right? So when the paramaterial is rock, there's going to be a lot of rock in the soil profile. Depending on the type of rock, of course, determines the soil texture, the depth of the soil profile, how easily weatherable it is, also the fertility of the soil profile, or just how naturally fertile any soil is. And specific to Idaho here, we mostly have igneous and metamorphic rocks as the paramaterials here. Soil profile forming from residuum, probably igneous or metamorphic, if we're thinking about the rock cycle. Not everybody here loves geology as much as I do, probably, but hopefully the rock cycle is familiar. Getting into some more specific, before we do that, this soil profile, what I really like about this one is just how diverse, appreciating the beauty of soil profiles, and they don't have to be all super tall, 1.5 meters deep. This one's pretty short. It was probably less than waist height on me. If it's a little bit familiar, you might have seen this picture before if you sent me an email. I made this my email profile picture on Outlook. This was a soil judging pit in Ohio a few years ago at the national contest, and it was just very little soil on the top of a little shoulder or summit of a bedrock kind of outcrop here. And there used to be a lot more soil before all the other teams started judging it, taking their samples from between these cracks in the rock. So if I'm thinking about the rockiest, the most residuum soil profile that I've ever seen, I think this one's probably pretty far up there. Really slow weathering. The texture is derived right from these kind of sandy quartz rocks here. Not a lot of soil to work with, but still worth appreciating. Bringing it back to Idaho, at least some of our Idaho rocks. Does anybody know, just by the picture, what this first one is going to be?
It looks a lot like basalt.
Basalt is correct. We have, just important in the geologic history of Idaho, of our region of Idaho, Washington, the Northwest, we have these basalt rocks. Basalt is an extrusive igneous rock. Igneous meaning formed from cooling magma, and extrusive meaning that the magma cooled outside of Earth's crust. So it was exposed to the atmosphere. That means it was really fast cooling. It has really mineral grain sizes. Like you can't see the individual grains necessarily in this basalt rock. So extrusive, fast cooling. The reason we have it is because of the Columbia River basalt. This is a really interesting geologic formation here in the really what's now the Columbia River basin, Columbia Plateau here. From about 15 to 17 million years ago, there were many events, not necessarily eruptions. It's exciting to think about like volcanic explosive eruptions in the igneous rocks, but this is more of like an oozing from a huge fissure or crack that opened up in Earth's crust, and magma just flowed out of it across the whole entire landscape, covering this all the way to Western Idaho, all the way west to the Pacific Ocean, really. And it's just many, many of these kind of magma flow events, lava flows that stacked up, not each one, maybe not very thick itself, but repeated events really kind of stacked up. We have a really important igneous rock history here. And interestingly, or what's probably most exciting about these basalt rocks are how you can recognize them driving across Washington, for example, is these really distinct column structures, the way that it cooled, created these just vertical, I don't know, they're like those long Tootsie Roll shapes just sticking up. Yeah, might have 5 or 6 sides. Sometimes I've heard some discussion about that, what makes how they're also uniform too. You know, they're all the same height, they're all the same. They can be different thicknesses, but really exciting to look at. This is like Drumheller Channels, I think, Central Washington, if you're driving across the state. Some really beautiful places to see these. Also the Lewiston grade, if you're going down to Lewiston, there's some really beautiful basalt outcrops. Actual soil that's formed from basalt is probably going to be clayey. It's going to have a lot of clay compared to some of these other bedrock types, but this one's relatively hard to find. I don't have any good soil pit locations that show like a basalt residuum paramaterial just yet. I'm still looking for them. Elk River that way. I've seen it on, yes, definitely a lot of basalt outcrops, like the whole, like the Clearwater River it is. That's a great place to see these. The soil series around here with basalt residuum like mapped in it, described in it. So I know it's around here. It's called the Cranberry series. So if you ever run into Cranberry soil series, maybe let me know. Let me dig a pit. It would be like a silty clay loam or clay loam texture class, probably with some of this basalt gravel in it. That's how I recognize basalt residuum. Moving on to our igneous rock, this one is granite, maybe looks a little bit more like a countertop. Whereas basalt was extrusive igneous, granite is an intrusive igneous rock, so still formed by the cooling of magma. Here, intrusive means it's cooling within Earth's crust, within the mantle probably, which means it cools much slower, cools over a much longer time, long enough that the individual grain size in this granite rock is much larger. They're more coarse. You can actually see these different mineral grains, intrusive igneous. And the reason we have a lot of this granite rock is because of our formation called the Idaho batholith. Batholith meaning like a magma chamber that either cooled in place or intruded on some other existing rock layer, and then it hardened, into solid rock, and then was brought to the surface either through erosion or some kind of uplift underneath it. There's 3 main occurrences of this Idaho batholith, and these 3 groups: Connexia, Bitterroot, Atlanta lobe. And it gives us a lot of granite paramaterials in the States, gives us a lot of like the desirable economic minerals. I think from this igneous kind of history creates the precious metals that had been historically important to our state's economy, but also it kind of explains the really rugged topography of the central part of Idaho, these rugged mountains, just how remote, how wild it remains. There's not much development there. There's only one road, right? Highway 95 that goes north and south here. There's nothing really in this middle part of the state. Thanks in part to this batholith and the effect it's had on the rugged topography and the difficulty to pay for development.
I was going to say, can we assume that the granite is harder than the vast majority of other similar rocks?
That's a good question. I don't specifically know about the hardness, but I suppose that's true. I mean, the resistance to weathering.
Weather.
Yes, I would definitely agree with that. Very difficult to weather. Another type of bedrock we have here that I think of as hard to weather is, or no, so before we move on, our granite age, this Idaho batholith, 70 to 100 million years old. And this one produces relatively highly fertile soils when you're able to weather it. Granite residuum soils, probably higher natural fertility. Compared to quartzite. Quartzite is not an igneous rock, but rather metamorphic. It's by definition metamorphosed sandstone. So if you imagine like sandstone sedimentary rock, grains of sand essentially that are accumulating somewhere in some kind of depositional environment, maybe riverbed or ocean floor, sand particles that eventually lithify, turn into rock, and then you take that sandstone rock and you cook it or subject it to intense heat or pressure or something. You bake the sandstone all together and then you get quartzite. As a result, quartzite rock is almost all silica, the silicon dioxide, SiO2, from all the sand grains. And since it's almost exclusively silica, it produces relatively low fertility soils. While this granite here is multicolored, it's got the potassium, the calcium, magnesium, sodium, maybe all these plant micronutrients that give this rock its, diverse mineralogy, diverse colors. That's going to result in the soil profile in the form of nutrients and fertility, whereas quartzite is really just pure sand. Not a lot of nutrients to go around there, and for that reason, they're low fertility soils. In the world of forestry, I know Mark Kimsey pretty well from our SOIL 456 North Idaho field trip. He likes to talk about good rocks and bad rocks. And is quartzite a bad rock? I mean, it didn't ask to be metamorphosed sandstone. It can't help the nutrient content that it has. So perhaps if it's really resistant to weathering, Mark Kimsey's comparison is forest growing on quartzite is like eating a diet of Coca-Cola and white bread, whereas more granite bedrock is like the steak and potatoes diet. So more nourishing, more fulfilling. Quartzite residuum would be really sandy soils, probably really shallow because it's difficult to weather this really durable material. Not very nutritious. Bad rock, I'll leave that up to you guys. A rock that I would agree on, if we want to talk about a rock that's really bad for plant growth, we could talk about serpentinite. Serpentinite's a real bad rock. This one's special. It's another metamorphic rock that specifically metamorphosed underwater. So some kind of sedimentary rock, probably in oceans, because we need water involved in the structure of this mineral. Exposed to some kind of heat or pressure, probably only found at like hydrothermal vents, so it's a little bit more rare. I don't think that we have it in Idaho necessarily, but this interesting metamorphic process results in naturally very low amount of nutrients and a very high load of heavy metals at the same time. So thinking about paramaterials, if the soil forms from the ingredients that the paramaterial provides, any soils formed on serpentinite are going to be not only not very fertile, but also potentially toxic to plants. And for that reason, the only plants that survive in these serpentinite ecosystems are specially adapted ones. This includes California aster, brome grass, foothill pine, siskiyou cypress, These examples come from California. I think this is kind of San Francisco, Sacramento kind of area where there's really not much plant growth to begin with, and the only ones that do survive are pretty specially adapted to it. We have a sample of serpentinites in the soils lab rock collection, so we'll get to see that in a couple weeks. We'll do a rocks and minerals activity. So not that any of you are gonna taste test or eat any of these rocks, but definitely don't take the serpentinite. It's my recommendation. Okay, that is our Idaho Rocks content, right? I could talk about geology all day long. I do have some more geology slides to go through. Maybe we'll save those for another time though, because we've only got 20 minutes left and a lot of paramaterials to cover. And even more than geology, I love glaciers a lot. So now we can start talking about glacial paramaterials. Really important where I was raised as a soil scientist, in the Midwest, but still very relevant to what we have in Idaho here. When we talk about glaciers, we have these multiple types of glaciers. Alpine versus continental, what's the difference really? Any glaciers we still have today, at least around here, are going to be of the alpine variety, forming in these kind of mountainous environments. Anywhere, this is true for all glaciers, how glaciers form. Anywhere you have really cold temperatures, snow and ice accumulating through the winter, that survives the summer, and then more snow and ice accumulates in the winter, that survives the summer, or continues accumulating all year round, perhaps. You have this accumulation of snow and ice faster than it melts, so eventually it's going to all freeze, coalesce together, and begin to flow, because it's water, but even though it's frozen, it still can flow like water. And it's going to work its way down and out of these mountain valleys, carving up the valley as it goes. And then maybe you have these multiple alpine glaciers all joining together to form something much larger, or you have just a continent scale glacial formation, maybe in northern Canada during an ice age. So then this whole entire wall of ice begins to just flow across the landscape. Then you have a continental glacier. What else here? Glaciers form in these cirque basins. It's really tiny on this diagram here, but at the top of the glacier really is what we call a cirque. These are now, after glaciers have melted, perhaps you have a lake left behind. These alpine lakes, or cirque lakes as we could know them as. Really, these glaciers just join together, they spill across the landscape, and we know there's been multiple advances and retreats of these glaciers over time. Multiple advances, and then each one is going to rework the landscape as it goes. It's really just a bulldozer plowing its way through everything in front of it. These multiple advances can be plotted on a map. This yellow one here across most of the northern U.S., how specifically glaciers relate to the lower 48, at least. This yellow event is the most recent one. It's called the Wisconsin glacial advance, not because it only happened in Wisconsin, or that Wisconsin was particularly important about it, but it just received that name because the best, or maybe either the best examples of it or the first descriptions of it took place in Wisconsin. Really, really beautiful effect on the landscape today. So beautiful. But then there's older ones too. Green is the Illinoisan advance, covers a lot of the state of Illinois. Kansan, Nebraskan. Nebraskan's hard to see, it's the red one here, but the Kansan advance, really the only glacial impact of Kansas is this pink advance. One of my favorite parts of, or why Wisconsin has a particularly interesting geologic history is this white spot right in the middle of the state there. Through all these, these are potentially 4 glacial advances. This one spot in the southwest portion of the state got missed every single time. I think it's still kind of a mystery why this specific region just never got covered up by the glaciers, but each one of these separate advances, which happened hundreds of thousands, millions of years apart in some cases, left this area untouched. So it's an even more particularly unique and beautiful. There's lots of bluffs, sandstone, cliffs, that maybe were forming everywhere else, but just got covered up, reworked by all these glacial advances. Really, really exciting stuff. Or the futures are first described, but it's easy to think about how like all these dramatic changes on the landscape and just exactly how long it takes. Like it's easy to think of all this stuff as a finished product. And glaciers and kind of the effort they invest in the landscape reminds me of, or I was reminded at least, 4 years ago now, back when this is when Joe Biden was running for president the first time in 2020. I was a fan of this political satire Twitter account that was pretending to be Joe Biden and telling all crazy Joe Biden stories. It was so-called Joe he was when he was still running for president. But one of my favorite tweets of this satire account was when he mentioned glaciers by name. It's complaining about just the political climate in general and both sides trying to get the entire ideology in at once through a debate or through some kind of big legislation. He says, look, you collect these ideas, you pitch them one at a time. It takes decades. It takes centuries. The government moves like a glacier, but it makes big changes like one too. That just speaks to me not only because it's glaciers, but also, I don't know, maybe I don't expect too much from the federal government, or I expect it to move really slowly. Progress is perhaps difficult to come by, but still undeniable.
Yeah, and while they're at it, oftentimes makes it more difficult for the people trying to live their lives.
I suppose, yeah. So maybe it's an advantage to make changes slowly, but still move like a glacier, but make big changes like one too. That spoke to me just from a government perspective. What else? The other thing I liked about this account was the replies. He's cracking skulls in his comment section. "I'll fill your chest with soil" was one of his particularly vicious comebacks, which made the original tweeter delete. Gotta love that. But there's a Joe Biden story if I ever saw one, when Barry and I once threw, this is honest, we threw this magic ring into a volcano, walked there to do it. It was awful, the entire procedure, but it needed to be done. That's sounds about right. Okay, back to Idaho and local examples, some local glaciation or where we can still see evidence of this, why it's relevant to the state of Idaho. Up in the Selkirks, we were just there a couple weeks ago on the 456 soil science field trip. We have multiple of these alpine lakes, these cirque lakes, if you will. They all are located on the northeast side of any given like mountain peak, on the northeast face of some of these peaks here, because that is the most shaded from the sun. It's the relatively coldest part of the mountain, receives the most snow and ice in a given year. That's where the glaciers themselves probably started to form and would have lasted the longest. And that's where we still have these lakes remaining as evidence. And you can see just the path each one of them took as it kind of flows down these valleys, which probably existed in the first place when we're talking about an erosional environment. Water's going to follow the path of least resistance, and then as it's building up steam, building up mass, carving out everything in front of it, carving out these valleys, you can just tell the path of the flow here until it reaches this much larger glacial valley here, the Kootenai Valley. And they all join together. Where are we here? So those are all alpine glaciers up in the Selkirks. You can still see these alpine lakes, cirque lakes. But then we also had some effect of the continental glaciation, right? We had, going back to this one, the Laurentide ice sheet, which covered most of Canada and the rest of the US. But here on the western side of the Rockies, we have the Cordilleran ice sheet. There's four main lobes, or if people ever talk to you about the four main glacial lobes here, we've got the Cordilleran on the west, which is most relevant to us. The Laurentide ice sheet technically is two. It's this Keewatin lobe on the kind of central Canada, and the Labradoran on the eastern side. And then The fourth one is not on here, but it's actually still around today. The fourth main part of this ice sheet is in Greenland. So this Cordilleran ice sheet relevant to us, it came through north from Canada down through in Idaho. This Purcell Trench is the geologic feature that's now like the Kootenai River Valley. Ice flowed down. It eventually dammed up the Clark Fork River and created this giant glacial lake, Missoula here, which is, of course, not a big lake anymore. From this dam that blocked the flow of the river, we create this massive reservoir of water, and then eventually, over time, ice doesn't really, it's not a very permanent solution if you're looking to create a big lake like this. The dam broke, a catastrophic, super dramatic failure. The whole entire lake drained out as much as it could. Floodwaters barreling across the landscape, scraping up, bulldozing themselves as like liquid water, all of eastern Washington, and turning it into what we know today as the channeled scablands. Super important, super interesting and exciting part of our our geologic history here in the Northwest. If any of you, I think we still have some of you that took Soil 206 with me as the instructor. I had everybody do like a virtual field trip interactive activity to learn about like a virtual field trip of all this stuff. I'll probably put that up again just so everybody else gets a chance to see these, see the activity, work through it, just because I'm such a big fan of it and just how awesome this whole glacial story is of the Missoula floods and how, I mean, the story itself of how they were described and how we came to understand them itself is really exciting. So now for specific examples, what we can find in a soil profile that's evidence of glaciation, if we want to build these glacial stories ourselves, one of our first options will be glacial till as a paramaterial. Glacial till is just any sediment that's pushed by the glacial ice. The business end of the glacier, you know, that bulldozer. The sediment that it leaves behind is generally very poorly sorted, which means it's all mixed up. It's like my dad, a little bit all over the place sometimes. It's got big rocks, it's got little rocks, it's got sand, it's got clay, not in any particular sorting or order, poorly sorted, and then also rounded rocks because these rocks have been pushed, they've been tumbled across the landscape, they're well worn from their many travels. So they probably don't match, if you know what the local bedrock is in any area, the rocks that you see in glacial till paramaterials probably will not match it because they've been moved a great distance from their source. Glacial till can really be any texture too. Sandy, loam, silty, clayey, really could be anything. But the rocks are really the main giveaway, I think, in the relatively low amount of sorting. I think both of these pictures come from the McCall area. We have glacial till paramaterial in McCall. When Jody, the past pedology instructor, was talking about these slides in glacial paramaterials, she had some horror stories to tell about doing soil research in the McCall area and how horrible the digging is there because of all these rocks. So her advice to everybody is, if you're ever asked to dig a pit in the McCall area, just say no. Let me do it instead. I would love to describe glacial till paramaterial anywhere I can have the chance. So probably McCall for the closest till area, or maybe halfway down one of those valleys in the Selkirks could have been glacial till. Anything that's pushed by the front end of the solid ice glacier. Riley?
What would you do to tell the difference between?
It helps to know a little bit about the landscape. We're going to get into alluvium coming up here. Another similar one that also might have rocks, also rounded, how you possibly tell apart, is glacial outwash. This is specifically sediment deposited by glacial meltwaters. Whereas till is unsorted, glacial outwash is well sorted, and it's usually sandy because we're thinking about sediment carried by flowing water. I'm thinking about like sandy kind of creek bottoms. And what's interesting is both the particle size and the rock size, whether or not you have rocks, depends on the energy of the water. So depending on how much, like the dynamics, of the glacial melting, how much water was available, how fast was the flow, determines a lot about the particle size we see. So taking kind of a zoom in, I talked about my uncle back home in Wisconsin who likes to send me the video of the floating W horizon, right? He likes to just help himself into like quarries and gravel pits on the weekend just to check them out, poke around, So this is one in southern Wisconsin. He noticed all these layers, wanted me to describe it, and it's a perfect example of sediment from an glacial outwash plain where you have these huge rocks right here. Imagine the amount of water, like this one specifically. Here's another big one, big rocks around here on the bottom. It takes a lot of energy for water to be pushing to flow through and carry rocks like this with it, but then maybe course of water changed, or there was just less water available. Maybe it was colder, the glacier kept advancing, or maybe there's another big melting event and it path diverted or something. And then we have much slower moving water here, putting down a layer of finer sand, maybe silt here, and it just can alternate back and forth sometimes between really finely sorted sand, and then you have more coarse, you have gravel in that layer, and then a big layer here of just sand, maybe silt, even if it's really slow moving water, and then finally back into a lot more coarse gravels and rounded rocks. Really beautiful organization to it. Not always necessarily flat, too, is the thing. He found another gravel pit, thank you, Uncle Mike, with these diagonal layers to it. This is probably from a really big outwash plain where we have like sandbars forming. So this diagonal form of these stream beds here, of the diagonal bedding, is probably from like a big sandbar in the middle of this. What used to be a glacial outwash plain is now just like a forested landscape. Pretty beautiful. When the sediment is even finer, or the water speed is even slower, maybe at the bottom of a glacial lake, we have lacustrine paramaterial. Lacustrine just means sediment deposited in glacial lakes. This is the most well sorted so far. There's probably no rocks. No rocks make it to the glacial lakes because they've all fallen out in the streams. So for that reason, this is usually a clayey texture. We might have varves possible. Varves are just these individual layers of like silt, alternating silt and clay paramaterial from an annual cycle. So there's a lot of turbulence in lakes, like storms, water flowing in. In the summer, you have silt settling out and forming on or collecting on the bottom of the lake. But then in the winter, let's say the whole entire lake freezes, the water becomes extremely still for months at a time, so long that clay particles can begin to accumulate on the bottom, settle out of the suspension. And then the cycle repeats. In the summer, you have silt. In the winter, you have clay. Alternating layers of something clay, right, are these varves. There's a closer up view of it. You can see some of the, in this example on the right, these alternating layers representing one single summer and winter cycle from thousands and thousands of years ago. I think that's really cool. This example we pulled out from, or we collected on the field trip 2 years ago, North Idaho SOIL's field trip. I was trying to collect some again just a couple of weeks ago. Nicole was along, Nicole joining on Zoom or watching later. She could tell the story of me waist deep up in a creek, trying to dig out with a shovel some more of this really gray varve containing clay sediments. It's a fun story. Next is loess, probably the most important one to us on the pollute set list. Any sediment deposited by wind. By definition, wind deposited sediments are extremely well sorted. There's going to be no rocks, because when you think of the amount of energy required by water to move gravel, big rocks, even more energy would be required for wind to do the same thing. So we have no rocks, usually very silty. It could technically be fine sand too, as less paramaterial. Important to us because it's what we have on the pollutes. those are the main glacial paramaterials with just a couple minutes left. I'll go through some of the non-glacial paramaterials relatively quickly. We have Aeolian sand as well. It's similar to loess in that it's deposited by wind, but this is specifically medium to fine sand, usually in dune environments. I think my brother took this picture in Africa would be the place I could think of on Earth, at least, with a lot of well, you know, water conservation is also really important here because of how dry they are. So these people are probably very interested in conserving water, and also low fertility too, because it's all silica and sand. Not a lot growing there, probably because it's water limited. The nutrients must flow. Another one we'd be remiss not to talk about in paramaterials here is volcanic ash. Any sediment ejected from a volcano, usually silt-sized particles, kind of famous or known for its really low density, carried really long distances by the wind, which is how we ended up with our volcanic ash here from the Mount Mazama eruption, now Crater Lake, Southwest Oregon. And the important thing about volcanic ash is its really unique chemical and physical properties that retains phosphorus really strongly, has a low bulk density, retains water as well. Really important for forest productivity or comparing stand productivity where you have volcanic ash soils versus where you might not. Can affect not only the growth, not only the height, canopy cover, also the species present because of the way ash retains water. So maybe I'll start next time. We have 3 to go: alluvium, organics, and colluvium. I'll pick up next time with those as we talk about time. But that'll do it for today. Let me know if you guys have any questions about tests coming up or any of our pedology content. Thanks, everybody.